All right, so we're now going to talk about the propagation of uncertainty. And what that's all about is typically if you want to measure something in nature, Planck's constant, say, you don't go down to Amazon and order a Planckometer and measure it, plug it in, and it spits out the value. You typically go in a very roundabout way to extract a particular quantity of nature via multiple measurements. And then you perform some operations on those measurements. You do some math, run it through some functions, and you spit out a value. But given the uncertainty in those measurements that you make, how does that translate to the uncertainty in the value you calculate of your final value? So you're going to measure a quantity. You're going to measure a quantity q, and say that's equal to some function of f of x, y, z, dot, 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 all the way down. It could be several variables. And then each one of those variables, or rather, let's write it this way. Each one of those variables has some measured value. We'll call it x naught plus delta x. Y is equal to y naught plus delta y, etc. And these would be the measured values that we had from last lecture. Now, that somehow has to translate to q is equal to q naught plus or minus delta q. We're going to have some uncertainty in the value of q that we measure. And that's what today is going to be all about. So let's figure out how that actually translates. We'll go through, first of all, some simple rules that you may have seen before. Namely, if you have q is equal to x plus y, there's a simple rule. You add the uncertainties. If q is equal to x times y, you add the relative uncertainties, and we'll justify all this. And we'll also talk about the difference in independent versus not necessarily independent errors. In other words, are the errors correlated? If not, which is often the case, you can more tightly bound your uncertainty, and we'll go through how that works. Finally, we'll derive a general formula that will work in all cases for representing your uncertainty of an arbitrary function. So let's get going on that. So in one of the previous labs, we might have had some Kirchhoff problem. We have V naught coming in. We might have had a diode and a resistor. And we wanted to infer, for example, the voltage across the diode. From Kirchhoff's laws, the voltage across the diode was equal to V naught minus the voltage across the resistor, which was IR. But let's just leave it this way, minus V through the resistor. And we make some measurements, and we find that V naught is equal to, or actually I'm going to call this V in. That might make things a bit easier. We'll call this V in. V in naught, that's why I call it V in, plus or minus delta V in. VR, we measured it to be VR naught plus or minus delta VR, okay? And we know that our diode voltage is the difference of these. So let's just ask, how bad could it possibly be? Given that we know that V in is between these values, let's assume that it's the widest possible range. And VR is between these values. How bad can it get? So V diode from these, we'll call it that the V diode naught, from these measured values is just going to be the difference of them. So that's V in naught plus or minus delta V in. Okay, so that's minus VR plus or minus delta VR. Now, I don't write minus plus here. I don't know which way it's going. It's completely random, either one way or the other. So we just leave it as plus or minus. It's still the case that it could be on either side of it with, let's say, equal probability. And I can rearrange this. V in naught minus VR naught plus or minus. Well, if they're both have, in this case, opposite signs, that could totally happen. That's going to bound our worst case scenario, V in plus delta VR, right? So if one's going up when the other one's going down, we subtract them, that's going to be our maximum error here. So this, in this case, is going to be our measured diode voltage plus or minus our uncertainty of that diode voltage. Okay, so let's write this a bit more generally. This is an example, a specific case that shows that if we just grind through it, the worst that's going to happen is we're going to get the sum of these two errors. So generally, if we have f of x, y, and it's equal to x plus or minus y, we can just write that as plus, right? Because y is just some negative variable, then it's x plus negative y. And x is equal to x naught plus or minus delta x. Y is equal to y naught plus or minus delta y. Well, then the rule tells us that our uncertainty in the function is just the sum of the uncertainties of the individual variables. If we had more than that, we had x plus y plus z, we just sum all of them up, right? So this is the uncertainty, this is the general rule for, or better call it the specific rule for adding uncertainties of a function when you're adding two variables. So let's do another simple case. Let's say that we have we've measured a current and a voltage and we want to get the power. Another example, we might, oh, that's a bad pen. Let's not use that one again. Another example, let's say we have power, which is the product of current times voltage, and we know that I is equal to I naught plus or minus delta I. V is equal to V naught plus or minus delta V. And we want to find out our power as well as its uncertainty, right? So we want power equals P naught plus or minus delta P. What is that delta P? Let's play the same game, okay? So we're going to play the same game. We're just going to grind it through. So that's equal to the two variables times each other, the product of the two variables, delta I plus V naught plus or minus delta V. And we're just going to say, like, how bad, let's just assume that everything's against us, you know. Fate is against us, and we're just going to get the worst possible case. These things are maximally big at the same time. Okay, so we're going to get I naught V naught plus or minus I naught times delta V plus or minus V naught times delta I plus or minus delta I times delta V. Okay? And the first thing, this is going to be our first approximation we make. We're going to assume that delta I and delta V are relatively small as compared to the product, right? So that these values are very small, they have small relative values, so that this term, the product of these two small values compared to this, imagine dividing everything through by I naught V naught, that this term here is going to be negligibly small. And this is an assumption we're going to work with for the entire remainder of this treatment of uncertainty, that we have relatively small uncertainties. If we don't, we just have to do brute force every time, okay? So let's continue. In this case, we don't have something that's quite as nice, do we? So we have, right away we have this term, which is P naught, and therefore this term is my uncertainty in power, okay? That's my uncertainty in power. And let's look at that. That's not particularly illuminating. So delta P is equal to I naught delta V plus or minus, we'll say plus or minus the whole thing, plus or minus V naught, what am I doing here? Plus V naught times delta I, okay? And it looks like kind of a mess, right? The delta V is times by the current and the delta I is multiplied by the voltage. So we can actually do a trick here. We can actually extract an I and a V, or in other words, we can divide both sides by the power. So delta P over the power we're going to divide both of these by I naught V naught. Okay, and when we do that, we're going to get some cancellation. So these I naughts will cancel. We get delta V over V naught, independent of I. Very nice. V naughts cancel here. Delta I over I naught, independent of V. So we just get the independent uncertainties. And this, if we recall from the last lecture, the end of the last lecture, this is the relative uncertainty, like the percentage uncertainty. So we have delta P over P naught, which is the relative uncertainty of our product, is equal to the relative uncertainty of the first variable, and we're going to absolute value it to make it the maximum possible value that it can be, times the relative uncertainty in the second variable. And that's a general rule, again, more of a specific rule, that if say if Q is equal to f of x and y, and that's just the product of two variables, and again, x is equal to x naught plus delta x, y is equal to y naught plus delta y, then delta q, or rather let's just write it fully, q is equal to q naught, which is just the product, xy, plus delta q, with delta q over q is equal to delta x over x plus delta y over y. In words, for the sum that we had before, the absolute errors add. For the product, the relative errors add. Okay? So these are special cases that happen sufficiently frequently that it's good to just know them. But we'll derive a general rule for this in a second. But before we do that, I want to talk about our pessimism. We're assuming the worst case scenario happens all the time. When the current fluctuates high, the voltage fluctuates high. When the current fluctuates low, the voltage fluctuates low. That means that these two things are correlated. But more often, these things are independent. I mean, maybe not. Maybe the current and the voltage are correlated. In fact, that could easily be the case if they're both driven by the same source. But often in experimental physics, you're looking at, say, noise from cosmic rays coming from space and noise coming from a cheap supply that you bought many years ago that's now misfunctioning and misfiring sometimes. These are independent things. Errors are often independent. So let's rewrite this rule for uncertainty, for adding uncertainties, when we assume that we have independent errors. So first of all, let's draw what dependent errors looks like. Dependent errors would mean that whenever delta x is going, say, positive, and I need to take a shopping trip soon to get some new pens, it looks like, then delta x is also, delta y is also positive. In other words, they add up. When delta x is big, delta y is also big. And that is when things are dependent, when things are correlated. This is dependence. Why dependence? Because the magnitude of one depends on the other one. Okay, they're correlated. Let's try to draw a picture of independence. Well, that picture graphically would look like this. I might have some value of x. I'm just abandoning this pen too. I might have some value of delta x. And this is going to contribute to the absolute uncertainty. But delta y is not going to add anything to delta x. Okay, how do we write that graphically? Well, it would be like orthogonal. Okay, so it's going to move up and down this way. It's not going to add any length to x. You know, a knowledge of x is independent of what y is doing. And we can draw that graphically this way. So that's, I'm afraid I only have two colors left now. My total error here, delta q, is equal to delta x squared plus delta y squared, all square rooted. Okay? They're independent. So delta x squared plus delta y squared equals delta q squared. By the way, this is called adding in quadrature. This is independence and we have what's called quadrature addition. Quadrature addition means they add orthogonally like this. We use the Pythagorean rule. Why quadrature? Well, this is kind of the way that sines and cosines go. They're 90 degrees out of phase, right? And if we remember, we mentioned it slightly briefly when we're talking about sines and coses, that we have the sine and the cosine quadratures. So that's kind of why this is called quadrature addition. They add like orthogonal quantities. Okay. So let's rewrite our rules now. If we have independence, q is equal to f of x, y is equal to x plus y. Well, then our delta q is now going to be a bit fancier. It's going to be delta x squared plus delta y squared, all square rooted. And this is always less than or equal to the sum of these two values, of delta x and delta y, equal to only when one of them is 0, right? So this is there's a triangle equality, which we won't go into here. But this is actually going to lead to, on average, a smaller error. Now, it could be bigger. We could get unlucky, and they could happen at the same time, and that's going to happen a certain amount of times. In fact, we're actually going to derive that in a lecture or two. How many times do we get outside this value? It turns out it's between 60 and 70%. About 2/3 of the time, we're going to get a value outside of this. But the majority of the time, the errors are going to be within this region if we have independent errors. All right, and then f of xy is equal to x times y. Then delta q is over q, rather, is going to add in quadrature the same way. Delta x over x squared plus delta y over y squared. So this is how independent errors will add up. They add up in quadrature. Okay, so we're going to use this assumption quite a lot now. If, by the way, just to reiterate the point, if we honestly don't know whether or not the errors are independent, we have to just use the absolute values, delta x plus delta y, all right? And relative plus the relative. If we use this, usually it's good practice to state we assume independence of the errors and add them up this way. So let's look at this whole thing. We're gonna look at this whole error analysis thing a bit more generally. Okay, so we picked particular functions. Okay, so again, we're going to assume that we have some function q of f of x is equal to f of x, y, z, dot, 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 all the way down. It's going to be some multivariate function. I can't draw in n dimensions very well on a two-dimensional surface, so it's going to draw it this way. But we're going to measure that, if you'll bear with me, at some point q naught. Given by we measured x is equal to x naught plus delta x. Y is equal to y naught plus delta y, all the way down. And then basically evaluating that function is going to land us right here. Okay? And for the particular measurements are. And we have to ask more generally now, if we wiggle all these parameters, if x wiggles a little bit, how much does q wiggle? Then if y wiggles, how much does q wiggle? And remember, they're all wiggling. And so q is going to be responding to all those variations all the time. So how much is q going to be shaking back and forth as all these parameters are individually shaking back and forth? So first of all, let's just say it in words. How would I describe that? Well, I would say that the expected change in q due to one of the variables, due to x, y, dot, dot, dot. Well, if we look at this, we see that is equal to how much q is changing. So the change in Q, in Q with that variable x or y or ... times, I have to truncate part of this function here so I can fit it, times what? Well, times the expected change in those parameters. All right, that's what it is. So basically we're saying, how much do we expect Q to change? Well, it's how much it changes with the individual parameters by how much those parameters are wiggling. That's what it is. So let's write this mathematically. We'll write this as delta Q due to a variable. X, say, is equal to, well, what is the change in Q with respect to just one of these parameters? This is the definition of the partial derivative. We hold everything else fixed and we just take the derivative with respect to that one variable. So this is df, Q is equal to f of these parameters, by dx times my expected change in x. Okay? And similarly, the change in y is equal to my expected change in f with respect to y times my expected change in y, all the way down. Okay, so delta is qz is equal to delta df by dz, or del f, del z, times the change in z. So that's what we're going to get. And basically what we're going to do is we're going to assume all of these things, for now, are independent errors. So my total change, we're just going to add up all these individual errors. So one thing we've done, by the way, we've kind of sneakily did this, is we've assumed these errors are small compared to the original value. What we've done is we've linearized it. That's not a word. What we've done is we said, look at the slope and multiply it by that value, by that amount of x, and that's how much Q is going to change along those directions. So we're actually assuming that our errors are small here, but that's about it. If we additionally assume that they are independent, we're just going to get my total error is going to be the sum of all these errors. And let's just add them up in quadrature, so that delta Q is equal to, let's write delta Q squared first, is equal to df by dx, evaluated at whatever we measured, squared times delta x squared, plus the change of the next one, evaluated at that value, y equals y naught, times delta y naught, plus ... And so the total change is just going to be given by this square root here. Okay, and this is the general rule for propagating uncertainties. We take the partial derivative of the function with respect to that parameter, multiplied by the uncertainty in that parameter, and we add them all up in quadrature. See if you can venture a guess as to what it would be if they weren't independent. Okay. My pausing there, I guess, is enough time for you to venture a guess. For dependent, it's just going to be the absolute value. Delta f by delta x at x naught. I'll just be lazy and write that as x naught. Delta x plus the partial with respect to y, delta y, plus ... Okay, and that's it. That's all there is to propagating uncertainties. Let's do two quick examples. Examples really help for this stuff. So we're going to remember this formula, and we're going to do two quick examples. The first thing we're going to do is just derive what we did kind of the brute force way before. Let's just say that f of xy is equal to xy. Okay? So f of xy is equal to xy, and we measure x is equal to x naught plus or minus delta x, and similarly for y, as we've been doing. So what's our uncertainty in f of x? We'll call this q now. Well, let's just apply our formula. Remember that here we have df by dx is evaluated at x naught is just going to be, well, y. Okay? And df by dy is going to be x. Okay, so this is an important point. Remember, y is a variable, so technically we're evaluating this at the measurement point of all our values, right? And this is going to be our partial derivatives, and we already know delta x and delta y. So let's just apply the formula. What does it tell us? It tells us that df by, or just delta f rather, squared is equal to the partial derivative, df by dx. So that's going to be y naught squared times delta x squared. And that comes from my df by dx times delta x plus df by dy, which was x naught times delta y, all squared. Okay? Now let's just square root it. So I'll remove this square. And that's it. But that kind of looks like what we want. But remember, our rule was saying that df, or rather dq, I better write it in the same way, so that dq over q, well, we're going to divide by 1 over q, 1 over xy. We'll put it in this square root here, and we'll get x naught squared y naught squared plus x naught squared y naught squared. Again, we're going to have a nice cancellation. This y naught squared cancels out with this y naught squared. X naught squared will cancel out with this x naught squared. And we are left with delta q over q is equal to del x, or uncertainty rather, of x over x squared plus dy over y squared. Okay? We already derived this, like just the grinding it out way, but I just wanted to show you that, first of all, those special rules that you might have seen before are just a special case of this general rule where we're adding the uncertainties in quadrature. Okay? Finally, let's just pick another function. I don't know. Let's just say we have an exponential decay. We have a decay rate, n is equal to a e to the minus b, we'll call it, little lowercase b. We don't know what that is yet. So what is our uncertainty? Given that a we measured, our initial population, if we're using this example, is equal to a naught plus or minus delta a. B is equal to b naught plus or minus delta b. Let's derive our uncertainty in n given these parameters. Well, we need to know the partials. So this is f of a b here is equal to n. So df by dA, well, the derivative of this will just give us e to the minus b. It's not independent of b. And df by dB is going to give us negative a e to the minus b. Okay, those are my partials. Let's just plug it into the formula. We're going to turn the crank and just see what we get. So delta n, my uncertainty in n, squared again, so I don't have to write a giant square root sign. We'll put it in a second, is equal to df by dA squared times delta a, and that's going to be e to the minus 2b times delta a, all squared. And we're going to have delta f by delta b all squared, which is going to be a squared e to the minus 2b times delta b all squared. And square root it to get the value. And this is our uncertainty that we'd get. We just have to plug in our initial values here, and this is the uncertainty we can get. We can leave it at that. Would it be simpler if we did relative uncertainty? I actually don't know. Let's try. Delta n over n naught is equal to, we're going to get what are we going to get? A e to the minus 2b in each case. I think we'll simplify. Delta a naught squared over a naught squared e to the minus 2b. And we get a cancellation. Okay, it's going to simplify a bit. Divided by this, a naught squared e to the minus 2b naught delta b naught squared over a naught e to the minus 2b naught. Oh, that totally cancels. So it gives us kind of a nice simplification. So the relative uncertainty is a bit more simple, but it's still not completely straightforward. It's going to be the relative uncertainty in A, it looks like, plus just the absolute uncertainty in B. Interesting. Okay, that's cool. But that's, you just take it on a case-by-case value, and we can do this with any function. If we measure something, we're comparing it to a functional form, we can propagate the uncertainties through the entire thing, just with partial derivatives. And we can treat it independently, meaning that we do this quadrature summing, or we can do it dependently. And I just want to leave on the board the general rule, just to stare at, is that if q is equal to f of x, y, dot, dot, dot. Actually, you know what? I'm going to be fancy. x1, x2, dot, 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 all the way up to xn. And then every one of those k's, xk, that might be 2, 3, 4, 5, is equal to xk naught plus or minus delta xk. Well, then my uncertainty in that parameter, the value, my best estimate of the value is just plugging in all the x's that I measured. And my uncertainty is given by the sum from k equals 1 to n, it looks like, of the partial of f with respect to xk times delta xk rather. And we evaluate that at k naught. If independent, and if we don't have independence, then it's just the direct sum. Okay, this sum looks fancier. Now let's do this. This sum looks fancier, but remember, it's just, we can just plug it in to see what it actually means. So remember what the last two examples were. So I'll say this is if not independent, if not. And that's pretty much everything we need to know about propagating uncertainties.